Oh, hi. So today we're given an equation whereby we're reacting 10 um, moles of aluminium with 6 moles of ammonium chloride, which will give us 4 moles of aluminium oxide, 2 moles of aluminium chloride, 12 moles of water, and 3 moles of nitrogen gas. So our first task is to identify whether the equation is balanced. So on the product side, on the reactant side, we have 10 aluminiums, which is gotten from there, and then we have six nitrogens. We have 24 hydrogens, which is we got by multiplying 6 times 4. And then we have 6 chlorines, and we have 24 oxygen gotten by multiplying 6 times 4. And that's our reactant side. On the product side, we have 4 times 2, 8, plus 2 aluminiums, and we get 10 aluminiums. So our aluminiums are balanced. And then we have 3 times 2, 6. So our nitrogens are 6 in the product side, and our nitrogens are balanced. We have 24 hydrogens. Our hydrogens are balanced. We have 6 chlorines, 2 times 3. And so our chlorines are balanced. And then we have 4 times 3, 12. And then plus 12, it's 24. So basically we have the same amount of atoms in the reactant side and in the product side. So that means our equation is balanced. And we're going to use this equation to calculate the maximum pressure that can form when 1,000 grams of ammonium chloride reacts with plenty of aluminium at 25 degrees Celsius in a 100.0 liter. And this is happening in a vessel. So the first thing I did is I laid out a strategy. So I am moving from grams to pressure. And in this way, I will first convert the grams of ammonium chloride into the moles of ammonium chloride, and I am gonna use that. I am gonna do that by using the molar mass as my conversion factor. And down here, I kind of found the molar mass of ammonium chloride, and I got it to be 117.485 grams per mole. And then that will give me the moles of ammonium chloride. And then I am going to convert that to the moles of nitrogen gas. And to do that, I will use my mole ratio, which is 6:3. And then I am going to find the pressure, and I'm going to use the ideal gas law formula to do that. So the ideal gas law is pressure times volume, which gives me when we multiply the number of moles times the constant times the temperature, it's gonna give me pressure and volume. But we just want pressure, right? So I isolated the pressure by dividing both sides by volume, and I am gonna find pressure by multiplying the number of moles times the constant and the temperature, and then divide all that by the volume. So I am gonna use the Henry's constant 0.082057, and then I'm already given my temperature, which is 25 degrees Celsius. But to use the ideal gas law, I have to convert the degrees Celsius into Kelvin, and I am gonna do that by adding 273.15, and I get 298.15 K, which is, 298.15 Kelvin. And I'm already given the volume, and the volume is in the right units, which is liters. So I put everything together in this table, kind of where I plan out my strategy. So the pressure of the nitrogen gas will be 100 grams. So this part of this table is kind of emulating this part of the strategy, and then this is part of the ideal gas law strategy part. Okay, so I put 1,000 grams of ammonium chloride, and I convert that into its moles by using the molar mass, and my units cancel, and I'm left with moles of ammonium chloride, and then I use the mole ratio, and I get the moles of nitrogen gas. And then I multiply that by the constant, which is this. And I multiply that by the temperature there. And then I divide that by the volume. And so this chart kind of emulates my entire strategy. And I plugged all of this into my calculator, and I got the pressure of nitrogen gas to be 1.041 atm. And you can see how I arranged my information into this table in a way that I'm only left with the units of what I'm looking for, atm. So my units cancel out. And now using this pressure, the third part is to find the concentration of nitrogen gas in water if the 1.041 was its pressure. I interpreted this as the question asking me to find the molarity. And I know molarity is the number of moles divided by volume. So this also calls for the use of the ideal gas law. And I laid out my strategy as the first thing to do is to find the moles of N2. And I'm going to use the ideal gas law, and I rearranged it to be the number of moles equals pressure times volume divided by the constant and the temperature. And then from that, I will find the molarity. So I am gonna assume that my temperature is 30 degrees Celsius, which I convert that into Kelvin by adding to 73.15, and I get 303.15 Kelvin. And I am gonna maintain the volume we were given at first, which is 100.0 liter. And my pressure is 1.041. And then I got this Henry's low constant of nitrogen in water, which I got from Peer Deck. And I'm gonna use the 1,600 liter atm per mole Kelvin. And so here I execute my strategy. First, I find the number of moles, and I plug in my pressure, and then I multiply that by the volume, which is 100.0. My volume, which is 100.0 liter, and then I divide that by the Henry's constant of N2, and I put the liter atm at the bottom, and then I put the mole K at the bottom. Since they're inverses, since this is an inverse, it will be right to put it at the top. And this will also help with the cancellation of our units, just so that we're left with the moles, which is what we're looking for. And then I multiply that with the temperature. So my atm cancel, my liters cancel, my kelvins cancel, and I'm only left with moles. And then I plugged this into my calculator, and I got the number of moles of nitrogen in 1.041 atm pressure is 2.146 times 10 to the power of -4 moles of nitrogen. And then I have the moles and I have the volume. So molarity equals moles over volume. So I put my moles, which is 2.146 times 10 minus 4, and then I divided that by 100.0 liter, and that gave me 0.000000215 molarity. And in standard form, that is 2.15 times 10 to the minus 6 molarity. Yeah, and that's gonna be the concentration of nitrogen gas due to a 1.041 atm per share pressure. Thank you.